Welcome to the Unit 3 Waves, Light and Sound End of Topic Test video mark scheme for Paper 4. Question number 1. Figure 6.1 shows a scale drawing of plane wavefronts approaching a gap in a barrier. On figure 6.1, draw the pattern of the wavefronts after the wave has passed through the gap. Now guys, when I taught you this topic, basically we get maximum diffraction when the wavelength, that's the distance between the wavefronts that you see here, and the gap are almost the same size. If the gap is much bigger than the wavelength, then we get minimum diffraction, and if they're approximately equal, then we get maximum diffraction. Now here, they're closer to being equal than being far apart. So what do you get? Well, the mark scheme is looking at a clear attempt at drawing semicircles, at least 3 of them, of the same wavelength by eye. Now, doing it in computer, it was a little bit challenging, but these should be nice and curved. I know this one looks a little flat at the end, but it should be nice and curved. And the wavelength here and here should be the same. Now, a way of doing this is maybe to mark with a letter lambda, remember the Greek letter for wavelength, even if you wanted to call it x or lambda here and perhaps here, because the examiner is going to look by eye to see if they look similar, and if they do, you get the mark. Part B. The wave approaching the barrier has a wavelength of 2.5 centimeters and a speed of 20 centimeters per second. Calculate the frequency of the wave. Well, frequency, the formula for speed, frequency and wavelength is V equals F lambda, but F equals V divided by lambda. In other words, it is speed divided by wavelength, which should give you 8 Hertz. Or 8 waves per second. The very last part, state what happens if anything to the frequency of the wave as it passes through the gap. Nothing. The frequency does not change. The frequency of a wave depends on its source and nothing else, as far as you're concerned. Part D, explain in terms of diffraction why a car radio may pick up a low frequency radio signal but not pick up a high frequency radio signal when the car is travelling behind a hill. A hill is an obstacle. Diffraction occurs around gaps or obstacles. If you look in my book, there is a similar example, or talk of a similar example. Now, what you need to understand is that high frequency means small wavelength, and low frequency means larger wavelength or longer wavelength. And the reason that a longer wavelength wave, or in other words in this case low frequency wave, will be picked up by the car is because the longer wave will diffract more, it will curve or bend round the hill more than a higher frequency, smaller wavelength wave. So the answer, low frequency signals have longer wavelength. Therefore they will diffract more around the hill. Question number 2. A water wave in a tank travels from a region where the speed of the wave is faster into a region where it is slower. Figure 6.1 is a 1/4 scale diagram that shows the wavefronts in the region where the speed is faster. Take measurements from the scale diagram, figure 6.1, to determine the wavelength of the water wave as it travels in the faster region. Now, I did shrink your exam paper for you, but if it was the full length exam paper, what you should have got is any value around about 67 millimeters between these 2 regions here. And then what you were supposed to do is then multiply that by 4 because it told you that it was a quarter of the actual size. So roughly 26 plus or minus 2 millimeters. So in other words, you could have said 24, 25, 26, 27, 28 millimeters for the full wavelength, or you could have done it in centimeters. Okay. The speed of the wave in the faster region is 0.39 meters per second. Calculate the frequency of the wave. Again, V equals F lambda. F equals V divided by lambda. Okay, so that's the speed of 0.39 divided by the wavelength that you found. So in the official exam sense, it was 0.026. And if you plug in the numbers, you get 15 Hertz. On figure 6.1, draw lines that indicate the positions of the wavefronts of the water wave in the slower region. Now, when you go into the slower region, the waves are going to change direction. Okay? Now, think about it. If they're going slower, then surely the waves lag behind the original ones. So there's the original ones. You're going in a slower region, they should be kind of following in behind it. Now, the diagram works because not only do they fall in behind, they're all parallel with one another, and in the slower region, the wave should be closer together, which in this case it is. State what happens to the frequency of the water wave as it passes into the slower region. Again, frequency is purely dependent on its source. It doesn't change. Question 3a, figure 5.1 shows a metal strip held in a clamp. The end of the strip is pulled down and released so that the strip vibrates. X and Z are the extreme positions of the end of the strip during this vibration. Y is the mid position. Explain what is meant by the frequency of vibration of the strip. Now, we're taught frequency is the number of waves per second. You can't quite say that here because it's actually talking about a strip. So basically it's the number of vibrations per second. The amplitude of vibration of the end of the strip, well, it's the distance between Y and X or Y and Z. It's the distance between the maximum in the rest position or the minimum and the rest position. In other words, YX or YZ. Question number 4. Two types of seismic waves are produced by earthquakes. They are called P waves and S waves. P waves are longitudinal and S waves are transverse. Explain what is meant by the terms longitudinal and transverse. These are straight definitions from any textbook, including my own. Longitudinal, oscillations or vibrations that are parallel to the direction of travel. Transverse, oscillations or vibrations of particles that are perpendicular or at right angles to the direction of travel. State another example of a longitudinal wave, knowledge and understanding, sound. And a transverse wave, any electromagnetic wave, any light wave whatsoever. A seismic wave has a speed of 7.2 kilometers per second and a frequency of 30 Hertz. What's the wavelength? V equals F lambda, lambda equals V divided by F. So when you rearrange here and you put in 7.2 divided by 30, you'll get 0.24 kilometers. You're welcome to change it to meters, and it really ought to be in meters, but it does allow you to leave it in kilometers. Part B. Figure 5.1 shows an electric bell ringing in a sealed glass chamber containing air. A student hears the bell ringing, then the air is removed from the chamber. State and explain any change in the sound heard by the student. Well, sound doesn't travel through a vacuum, so the sound that the student hears theoretically should be non-existent, but in reality will just be much quieter because sound doesn't travel through the vacuum. Question number 5. Explain what is meant by total internal reflection. Here, reflection in a more dense material where there is no refracted ray, or words to that effect, or all the light in the more dense material is reflected. What is the critical angle? The greatest angle of incidence at which refraction can occur, or the angle of incidence where the angle of refraction is 90 degrees. Now I had to put that further down here because there wasn't enough space above. Part B, figure 7.1 shows a ray of light travelling in air incident on a glass prism. The speed of light in air is 3 times 10 to the power of 8. Its speed in glass is 2 times 10 to the power of 8. Calculate the refractive index. So refractive index is speed of light in air or vacuum divided by speed of light in medium or glass. You're going to have 3 times 10 to the 8 divided by 2 times 10 to the 8, which gives you 1.5. Now, quite often students here will get 1.5 times 10 to the power 16. That's because you're not putting brackets around the 3 times 10 to the 8 or the 2 times 10 to the 8. May I suggest making your life easier and using the EXP button or the times 10 to the power button, which is found at the bottom right hand side of the calculator next to the equals. This allows you to ignore the use of brackets because it will work without putting in brackets. Show that the critical angle for the glass boundary is 42 degrees. Well, the formula for critical angle is sine C equals 1 over n. You've just found the refractive index. So when you rearrange that formula and you calculate it, basically C will equal 42 degrees. So it's 1 divided by 1.5. That will give you a decimal. Shift sign answer, and that will give you 42 degrees. So the critical angle of the glass block is 42 degrees. Part 3. On figure 7.1, draw carefully, without calculation, the continuation of the ray through the prism and into the air. For convenience, I've copied and pasted the diagram from the previous page into this one, and this question always pretty much encounters a student mistake towards the end. How does it work? Well, most students did get this part right. When the ray of light hits the glass at 90 degrees, the first ray goes straight through. Then by I, you're supposed to draw a normal, and then the angle of incidence will equal the angle of reflection, and this is where it starts to go wrong. It's not perfectly 90 degrees, you know, like the whole thing. It's not 45 and 45. So by I, the angle of incidence and reflection should be the same. Put in another normal, and here it doesn't quite hit the glass at 90, so the light will bend away from the normal. Now, most students get the first one right. They almost got the second one right. What most students did was this red line here. And if you draw that line, then I hope you can see the angle of incidence and the angle of reflection are not the same. That's why it's got to be the blue line. And at this side, it doesn't go straight through because it doesn't hit the glass at 90 degrees like it did over here. So it doesn't go along the normal over this side like it did over here if I drew a normal. Therefore, more dense to less dense, light bends away from the normal. So no change in direction at the first pace, total internal reflection at the second. Angle of incidence should look equal to the angle of reflection by I, and then the refraction is greater at the lower face. Question number 6. Figure 7.1 represents an object O placed in front of a converging lens. State the full description of the image I. They want all of it. Virtual, upright, magnified. You needed at least 3 of them to get full marks. If you missed any one, you lost 1. If you missed 2, you lost 2. And if you contradicted any one of them, you lost a mark. Using the letters on figure 7.1, identify the focal length of the lens. Guys, the focal length is not the same as the focal point. It's the distance between the center of the lens and the focal point. So it's R to S, not just S. S is where the focal point is located. It's not the focal length. Figure 7.2 shows an object placed to the left of a converging lens. A principal focus of the lens is at the position marked F. On figure 7.2, draw 2 rays to locate the image of the object O. Draw the image. So remember the rules in no particular order. Apologies, missed a part here. On figure 7.1, draw an eye suitably placed to view the image. The eye should be down here, so you're looking at the image up there. I missed that out. Back down here, remember the rules. In no particular order, a line from the top of the object to the center of the lens, and then a line from the center of the lens through F and keep going. A line from the top of the object through the middle of the lens and the principal axis, what I call the middle of the middle. Keep going. Where they meet, that is where you will find your image. Part 2 says on figure 7.2, draw one other ray from the upper tip of O to the image. This is in your book, and basically they're wanting you to draw a line in reverse. And what you do is you go straight back along to the center of the lens, and then from the center of the lens you go all the way back to the object. Why? Because all the lines from the object and the image should meet. Whether it's 2 lines, 3 lines, 50 lines, they should always meet. And the one thing that I've forgotten to draw here is the actual image itself. There should be a line with an arrow that goes down, and the arrow should be upside down, and then you should always label it I for image. Question number 7. A ray of light passes through a length of curved optical fiber. Draw a diagram showing the fiber and the path of the ray of light. Well, basically they're looking for a fiber optic at a slight angle, where the angle of incidence should equal the angle of reflection, so you get total internal reflection. They then asked, describe one use of optical fibers in medicine. You may draw a diagram. It's probably wise to draw a diagram, and there are quite a few uses. What are they looking for the marks? Any mention of light travelling down the optical fibre into or out of the body. The idea that we use that light to examine the internal organ, because part of the light is reflected back up the fibre into our eye. Or we may use it to destroy cells by heating. The endoscope or the fibre bundle is inserted into the body to view an internal organ or for keyhole surgery. So basically they were wanting a rough idea of light travelling down the fibre and coming back up, total internal reflection. The idea that it's to either view something or to kill something, and the name of the actual process, and that would have got you the 3 marks. Part B. Draw a straight line from each wave on the left to the most appropriate speed. Well, light in air travels at 3 times 10 to the 8. Microwaves in a vacuum also travels at 3 times 10 to the 8. All electromagnetic waves, all light waves travel at 3 times 10 to the 8 meters per second. Sound, if you look at my book, is roughly 6,000 meters per second, and that's where the 3 marks came from. The refractive index of a block of glass is 1.5. Use your value of the speed of light from B to calculate the speed of light in the block. We've used this formula earlier in the test. Refractive index equals speed of light in air or vacuum divided by speed of light in glass or medium. If you rearrange this, you should find the answer is 2 times 10 to the power of 8 meters per second. No unit, you will lose a mark. Question number 8. Figure 7.1 shows a ray of monochromatic red light in air incident on a glass block at an angle of incidence 50 degrees. State what is meant by monochromatic light. Monochromatic light is light of single wavelength or single frequency. Although technically it kind of means one color, you shouldn't see it in the exam because a particular color can actually have a range of wavelengths. For this red ray, the refractive index of the glass is 1.2. Calculate the angle of refraction. Well, n equals sine I over sine r. Sine r equals sine I over n. Sine of 50 divided by 1.52 will give you some sort of decimal. Shift sine answer will give you 30.26 degrees. Without measuring angles, use a ruler to draw the approximate path of the ray in the glass block and emerging from the block. Well, less dense to more dense, it's going to bend towards the normal. At the other side, I'd draw a normal. More dense to less dense, it bends away, but not only does it bend away, the incoming ray in a rectangular block and the outgoing one have to look parallel to one another. So bending towards and then bending away, but looking parallel. Why is that? The angle of incidence here and the angle will give us an angle of refraction. That angle of refraction of 30.26 is the same as the angle of incidence at this point, which would also be 30.26. This is an angle of incidence of 50, but for this surface the angle of refraction should be 50. Hence the incoming and outgoing ray are parallel. The red ray in figure 7.1 is replaced by a ray of monochromatic violet light. For this violet ray, the refractive index of the glass is 1.54. The speed of light in the air is 3 times 10 to the 8. Calculate the speed of the violet ray in the glass block. We've used this formula a couple of times now. Refractive index equals speed of light in the air divided by speed of light in glass. If you rearrange, because you've already got the speed of light in the air, you should get roughly 2 times 10 to the power 8. Or in this case, 1.948 times 10 to the power 8. You do not need to leave your answer in standard form. However, units are important. Part 2. Use a ruler to draw the approximate path of the violet ray in the glass block and emerging from the block. Make sure that this path is separated from the path drawn for the red light in A part 3. Mark both parts of this path with the letter V. Now, just to make life easier, I've copied and pasted the diagram from the previous page. Not only that, I've put in the red ray that I drew in the previous page. So what you're supposed to understand from the triangular prism, Richard of York gave battle in vain, or red, orange, yellow, green, blue, indigo, violet. In other words, violet bends more, so it's closer to the normal. And then again, it'll bend away from the normal from more dense to less dense. So it should be parallel to the incoming ray at 50 degrees. Now, I didn't label this violet. You should. And the reason I didn't is because I've kind of given it a purple colour to indicate violet. But the exam asks for it to be labelled with the letter V. Therefore, you should label it with the letter V. The key is to understand that it bends more towards the normal, and then when it bends away, the red and the violet ray should be parallel. Question number 9. The following list contains the names of types of energy transfer by means of waves. Which one of these is not a type of electromagnetic wave? Well, that's sound, because all the other ones are light waves or electromagnetic waves. The nature of the wave that we've just named is longitudinal wave or a mechanical wave. The remaining names in the list are all regions of the electromagnetic spectrum, but one region is missing. Now this is purely memory. Which region is missing? You're going to have to revise. It's ultraviolet or UV. Part B. A television station emits waves with a frequency of 2.5 times 10 to the 8 Hz. Electromagnetic waves travel at a speed of 3 times 10 to the 8. Calculate the wavelength of the wave emitted by the television station. State the equation you use. V equals F lambda, or in this case lambda equals V over F. Plug in the numbers, 3 times 10 to the 8 divided by 2.5 times 10 to the 8, and you get lambda equals to 1.2 meters. Question number 10. Figure 6.1 shows white light incident at P on a glass prism. Only the refracted ray PQ is shown. On figure 6.1, draw rays to complete the path of the red ray and the whole path of the violet ray up to the point where they hit the screen. Label the violet ray. So I'm going to show the red ray first. If I drew a normal, which I haven't in this case, the light would bend away from the normal towards the screen. And then the violet ray, you have to understand, actually refracts inside the glass prism. This is very often badly done by students. They think the violet ray only refracts once it comes out the glass. So it bends towards the normal inside the glass, and when it comes out it bends away. It refracts even more. Why does it refract more? Because it has a bigger change of speed. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo and violet. So violet bends the most, but it bends inside the glass as well. Part B. The angle of incidence of the white light is increased to 40 degrees. The refractive index of the glass is 1.52. Calculate the angle of refraction of the red light. N equals sine I over sine R. Sine R equals sine I over N. Plug in the numbers, you'll get a decimal. And then when you do shift sign of that decimal, you'll get 25 degrees. Now why do you do shift sign? Because we want R, not sine R. State the approximate speed of the light incident at P. 3 times 10 to the 8 meters per second. The red light after it leaves the prism at Q, also 3 times 10 to the 8 meters per second. But no units, and you will lose marks. Question number 11. 2 students are measuring the speed of sound. The students are provided with a starting pistol, a stopwatch and a long measuring tape. The starting pistol, when fired, produces a loud sound and a puff of smoke at the same instant. Describe how the students use the apparatus and how they could calculate the speed. You may draw a diagram. Now I would recommend a diagram here. What you want is maybe a picture of the pistol, double-headed arrow showing the distance, and at the other side a stopwatch. And then what happens is when the person fires the pistol, the person with the stopwatch will see the puff of smoke start the stopwatch and then hear the sound and stop it. You've used the measuring tape to measure the distance. You've already got the time, and then by doing speed equals distance divided by time, you can find the speed of sound. Now there is another method which I'll let you read. But I would stick with method number 1. I think for me that's a more preferable one. Both are described in the book in terms of the second one as an example, but method 1 has an example and is described as it should be done. Part B. A device at the bottom of the sea emits a sound wave of frequency 200 Hz. The speed of sound is 1500 meters per second. Calculate the wavelength of the sound in seawater. V equals F lambda again. Lambda equals V divided by F. So you've got the speed here as 1500 divided by the frequency 200, which gives us 7.5 meters. Notice there's no divide by 2, it's not an echo, it's coming directly from the bottom. Part 2. The sound wave passes from the seawater into the air. State what happens, if anything, to the frequency. Absolutely nothing. Remember, frequency depends on the source and not what the wave travels through. The speed will decrease as it passes from the seawater into the air, because remember, sound travels fastest in solids, then liquids, then gas. Because in gas the molecules are further apart, the sound will travel slower. But remember, light travels faster in air than it would in water. I hope that makes sense, and I hope you found it helpful.